Hello?
Hello.
Yeah.
Pamir, on
Hi, Nagaraj. Just wanted to check if you can hear me.
Yeah, I can hear you.
Okay.
Hi, Pamir.
Hi. Welcome.
Yeah.
Just wanted
Thank
to
you.
check if you can hear me.
Yeah, I can hear you. I can.
Okay.
Hi, Pamir.
Hi. Welcome.
Yeah.
Just wanted to check if you can hear me.
Yeah, I can hear you. I can.
Okay. Hi. Welcome.
Yeah, thank you. I think some echo is there. I'll just close
Yeah, it's been repeating. I
Yeah.
just, probably because the YouTube was on.
Yeah, I opened YouTube also. That's why I think.
Yeah, same here. But yeah, we can start in 5 minutes then.
Yeah, I will just share my screen just to see whether everything works fine or not.
Mhm.
You can see my screen, right?
Yes, I can.
Okay.
Okay, we'll start in 2 minutes.
Yeah, sure.
Okay, so we'll just start. Um, so good evening, everyone, and everyone present here virtually today. So this is the second webinar of the Assam Artificial Intelligence Initiative on Generative Adversarial Networks, or GANs. And first of all, I welcome all of you on behalf of the team. So I'll just start with a brief introduction about I, or Assam Artificial Intelligence Initiative. So it's an initiative to promote artificial intelligence in Northeast India. And the goal is to build an academic network for students, researchers, AI enthusiasts to exchange knowledge and ideas, and also to make AI more popular among um, the younger generation and non-specialists in this region. And today we are delighted to inform you that we have Dr. Nagaraj Adiga, a senior research scientist from Zapr Media Labs, which is in Bangalore. And he will enlighten us about GANS today and its application in speech technology. So Dr. Adiga is currently working on GANs and autoregressive architectures for different speech applications like enhancement, recognition, synthesis, and voice conversion. He did his PhD from IIT Guwahati in the area of text-to-speech conversion. And his research interests are machine learning, signal processing, speech processing, biomedical signal processing. And also, before joining Zapr Media Labs as a research scientist, he worked as a postdoctoral researcher in Greece and as a signal processing engineer in Apple in developing neural-based text-to-speech systems, especially in noisy scenarios. So in this talk, Dr. Adiga will discuss about GANs and its applications. And Nagaraj, I'll hand over to you then now.
Yeah. Thanks, Pamir, and Assam AI Initiative actually. So this is a wonderful opportunity for everyone, and also since during this pandemic situation, so this is a good opportunity to learn remotely and get enhanced about the latest technologies, especially in AI. And this is a very good initiative. So I will just share my screen. I think it's shared already. So I will just share. You can share, see my screen, right?
Yes.
Yeah. Yeah. So today we'll discuss about generative adversarial network. So basically, this is a brief introduction. Since its audience is very general in nature, and some applications like where we can use GANs and how to train the network and some simple demo. And in between, if you have any questions, please ask so that the session can be more interactive, either through the YouTube channel or through since some of you joined through the Google Meet, you can just unmute your speaker and ask questions if you have anything in between. Okay, so what I planned is first I will give some brief introduction about GANs, why actually it's there and when it came, and how to train this network using GANs, and some simple demo using for image synthesis task, and what are the different types of GANs, and some of the issues and how to train these networks and tips actually to train. And then finally we can take some question and answers. So before starting actually, I will just take some toy example. Like for example, how to train like a neural network with to generate the images. For example, in this figure, I have shown actually the images from MNIST images, which is consisting of different variations of images like 504 along with the labels. So these are some data we have. Can we generate different kind of these numbers in different variations? Not only generating this, and how to, because we can write these images in different style, right? Like each people write in different ways. So we can generate this kind of images. So any neural network can be used or like any complex transformation, we can use it to train the network and to generate this kind of images. For example, we do some transformation. where input will be some noisy data or images, and from that noisy data we can do some transformations and to get some image. So we try to generate some synthetic images. So this can be done through the different neural networks like feed forward neural network or convolution neural network or variation autoencoder or autoregressive models. There are different tools are there. You can imagine like some like in signal processing background, like we can see that like to analyze that signal, we can use different transformation like Fourier transform or Z transform or Laplace transform. Similarly, we can here to analyze the data or the to synthesize the data, we can use different tools. Different tools are different neural networks like feed forward neural network or convolution neural network or variation autoencoder or autoregressive models. So we can imagine these are different tools to analyze the data. So, but what is happening is, in spite of all using these tools, the quality is still not good actually. That's why what they done is they propose a new network called GAN, which is proposed by Professor Ian Goodfellow and his group in 2014, which is basically consisting of two neural networks. One is generator and another is a discriminator. If you remember the previous image, so what in the previous images like a simple feed forward neural net, what they does is feed the noisy vector actually to the generator and we get some synthetic image. But in the GANs or generative adversarial network, we have two networks. One is a generator, which will generate the fake images like this, and another network called discriminator, which will tries to distinguish between the fake image and the real images. So basically, compared to the conventional networks, here we have two neural networks called generator and discriminators. And again, this comes under the family of generative models. And the objective function, the loss function, we use it called adversarial loss. What is adversarial means? Acting against each other. So generators tries to fool the discriminator by generating images which is very close to the real images. Whereas discriminator job is to fool the generator and distinguish between whether it's a real image, whether it is coming from the real images or it is generated from some neural network. So that's kind of learning is called adversarial loss actually, or acting against each other. So discriminator is going against the generator, whereas generator is trying to generate images which is very close to real images. So this kind of learning is called adversarial loss actually. How to learn this loss, I will tell in the next slides actually. So since in the conventional neural network, what we do is after generating the image, we compare against the real images itself, either using L1 loss or L2 loss, which is a user-defined loss functions. But here what we do is we use one more neural network called discriminator, which will do the like a data-driven based loss function. So the quality of the generated image will be very good actually, or we can get very like high quality images we can synthesize. So that was by that motivation that started this kind of network, where basically they have two networks, generator and discriminators. So this is very basic introduction. In the previous and in the next slides, I will mention how mathematically we can model it or how we can train the network. So for example, what they done is like it started in 2014. And then people started using for different applications. Initially, they started with images, but then used for the video and speech and all the applications. So, like initially, this is the plot which shows a number of paper presented. Like from 2014, you can see that from the 2016 it's picked up and it's exponentially increasing. Till 2019, it's all around like 500 papers per year, and just for GAN and its different applications, how it's going on actually. That's how this network is very popular. So you can get the more details about this in this link also, like what are the different types of GANs are used. Just from that link, actually, you can see that nowadays GANs are they started giving new names, actually some alternative GANs. So they started giving nomenclature from A and it's going till all the letters. Like for example, it started from A GAN, B GAN, like C GAN, like it's completely covered. For example, if you see the one which starts with S, actually there is a SGAN for synthesis, and one for stacked generative adversarial network, and one for the alternative training approach SGAN. So can see the how much popular this GAN network. So basically what we are understanding is like this is a new tool, and we can like what are the different application we use for the feed forward network or CNN. So same thing we can apply using it using the GAN, and we can get slightly better results. So that's the basic motivation to use the GAN actually. So and where all we can use it actually. So as I said, actually we can use it for the generating the data. For example, audio or the image or video. We can use it for generating this kind of data and variations of data. Usually what happens is by training we can get some kind of data, but can we generate the variations with it? That so that can be do it using the GANs. And also for the image editing, to convert from photo to emojis. So you can see that in Apple phones, you can see that by giving our photo, it can convert into emojis, or like text to image translation, or to generate the cartoon characters, or increasing the resolution of images, or even like face aging. Like nowadays in Facebook, you can see that there's a popular app called like if you give our image, it will tell after 20 years how we see actually. That is all coming from GAN actually. So there's some application I can just visually show it actually. So for example, for generating cartoon characters, we can get the variations in the hair length or color in the styles, or a different cartoon character we can generate it, that is using GANs. Also, for example, if you give the input condition of day, and it can predict the night condition using the GANs actually. So this is a ground truth, but it generated this kind of images. Or like we can, if you give the structure of a bag actually like this, it can fill the colors and give the image of vanity bag or something like that. Or like for example, like you can convert from text to image also. So there are a lot of applications, and visually you can see it here actually. So this link is also shared in the slide. And also, for example, I was saying photos to emojis, right? Like if we give our photos, it can convert into emojis. So it can be do like this, or like we can convert like improve the quality of the images from this image to this kind of image. So these are the different applications we can do it using the GANs. So this is like a brief introduction actually. So if you have any question in between, let me know actually. Hello.
Yeah, we are hearing.
Yeah. So if you have anyone has any questions about this basic introduction, you can ask, or I will continue for next section. Okay, so I will move to the next section.
I think we don't have any questions so far. So
Just continue. I think can take later.
Yeah, sure. Yeah, so we can take in end also. Just like because if something is missed actually in the beginning, so you may like lose that information in the end, right? So that's why I just asked if something is not understand, it will be keep haunting actually. That's why I just asked. Yeah, so I will go to the next section. That is how to train the GAN network actually, and what type of loss function we can use it. So as we know actually that we can do many cool applications using the GANs, but how to train this kind of network? So this is like two networks I told actually. One is generator network, and another is a discriminator network. So for example, imagine here actually this is the bottom one is the generator network, and the top one is the discriminator network. This network is similar to the right side network, just to show for the two inputs, a real image and the fake images. I just put it twice actually, and this is taken from the Ian Goodfellow paper also. So what basically we are doing is we randomly sample the noise vector and pass it through the feed forward network. In this example, we shown the 3-layer network, and we generate a fake image. And this fake image we are again passing to the discriminant network. So which is again a 3 layers, and it will output some probability value. So a generator job is to make this image as close to real image. So it tries to output the value of 1 actually for training the generator network. Whereas for a discriminant network, so first we feed the real images. We randomly select from the bunch of examples. So we randomly select some batches and feed forward it through the network actually, this network. And we get some value. So for real images, discriminator is tries to output the value of 1. And for the fake images, which is coming from the generator, so it tries to make it to 0. Whereas generator tries to make it the value of this fake output of the D to 1 actually. So basically it is acting against each other. So that's why it is called adversarial loss actually. So in order to further how actually mathematically it looks actually. So first what we do is input the noise vector, that is Z actually, through the generator network. And with the parameters of theta g. Theta g represent the weights and the bias, and we get some fake image, and then again this fake image will be passed to the discriminant network with the parameters of theta d. Theta d is the parameters of discriminant network, and discriminant network will tries to assign some score actually. So discriminant network output will be between 0 to 1, and which will like if it is a 1 actually it will be 0. It will be between 0 to 1, and if it is 0 it will be fake image, and it will be, if it is 1 it's a real image. The discriminator basically act like a classifier kind of objective function. So for example, for a given noise vector, if imagine one noise vector if we take actually and pass it through the generator network, so we get a fake image. So generator job is to maximize this function, and we are using log operation just to reduce the dynamic range. We have to maximize this function to make it equal to 1 actually, or if you write 1 minus of that, then we are trying to make the minimization of this problem actually. So just for mathematical simplicity, we are writing 1 minus of that, and this is done for one image actually. So we have to do this for all the set of possible values of Z. So that's why we are using expectation operator here. So we pass it all the possible images through the generator, and we get a fake images, and again pass it to the discriminator. Basically, we are trying to maximize this value for training the generator network, or minimization of this actually. 1 minus of this will be minimization, we are doing it. And log operator just to for the simplicity and reduce the dynamic range, we are using it. So that's how the loss function for the generator network is defined. And since we are doing minimization, so the minimization operator is used here, and the parameters of generator will be theta g. So this is how generator is trained. And for a discriminator, there will be 2 inputs. One is the real image, that is X actually, which will be passed to the discriminator, and another input will be noisy vector, that is Z actually, which will be passed through the generator to get a fake images, and again it will pass to the discriminator, that is d of theta d. So basically the task of the discriminator is to assign high score to the real images. The first image will be there, right? For that, it will output value will be very high, or it is close to 1 actually. And for the fake images, it tries to give as low as possible, or 0 actually. Ideal case will be 0, but it will tries to minimize the low score value will be given actually. And we have to do this for all possible real images, and as well as for the fake images. So we have to do for the while training, we have to, whatever the data we have, we have to do it for all the possible real and fake images. So basically, same as previous explained, here actually the left hand side of the equation 2, which represent for the real images, we are passing the real image through the discriminator, and basically we have to give the high value to this one. So we are doing that maximization and do it for the all possible data actually. Similarly, in the right hand side is for the fake images. So we randomly select the noise vector, pass it through the generator, and again pass it to the discriminator. This value has to be minimum or low value. But if you write 1 minus of that, again we are doing the maximization, because it's an inverse operation. And we are doing that 1 minus of this so that we can take maximization operation in common. That's why we are taking that operation. So this is about the how to train the discriminant network. So this is actually just a mathematical representation. So if you are if you feel that it's too much mathematics, I will just in the next slide I will show actually. This is a simple steps actually written in like how to write the code actually. So we have to train this network for the number of loops actually. So first we randomly select the noise samples and also the randomly select the real images, pass it through the discriminator, that is the left hand side of equation, and also fake images will be generated by injecting the noise vectors, and we get a fake images. And here the equation is same as the previous one, but just we expanded that to for the all possible images. So this is how we are doing the training of the discriminator. Basically we are doing the maximization or ascending in the loss curve actually. So all the parameter is going in ascending, all the theta d parameters will be ascending in the loss curve. Whereas for the generator, what we do is we randomly select the noise vectors, again pass it through the generator network, and we are trying to maximize this or minimization of this operation. That's why we are descending in the loss curve actually. So this is for one loop. We have to do it for multiple iterations to train the network, so that network can generate the images, the whatever the previous slide I showed, right, images, so that we can generate it. And basically what people do is more number of iteration they do it for discriminator within the loop. For example, they train 5 times discriminator and then 1 time generator, and sequentially they do this kind of training so that all the parameters will be trained properly. So this is the summary of GAN training. So just to illustrate actually how it looks, for example, this is the noise vector. It has to map to the real images actually. So for example, this is the actual data distribution, dotted line. The plot shown in the dotted lines is the data distribution, whereas the plot shown in the green color is the model distribution. So we are initially when the model is not trained properly, that is poor fitted model. So both the curves are in diverged actually, and the discriminator output also you can see that it is not proper actually. It is not same actually. So what happens is after updating the parameters for the discriminator, so you can see that the model distribution coming close to the data distribution, and after updating the parameters of generator, it still comes to very close actually. So and after doing this for several iteration, you can see that the equilibrium will be established actually. So model is fitting to the data distribution, and also the discriminator output will be comes around close to 0.5. When it comes to close to 0.5, then is either it's not able to say that the image is real or it is fake. It's in between. Then actually the training is done very completely, or proper training is happened. Usually it doesn't happen, but this is the ideal case. Like we can get the 0.5 score. So this is about how to train the GAN network. Any questions here? I'm audible, right?
Yes, you are. I don't see any questions showing up in the chat, so.
Okay, fine. Yeah. Because since it's one-way interaction, so I thought like maybe I'm disconnected, so just ask.
Yeah, I think maybe, yeah, I can pop in and out, just letting you know.
Yeah, okay, fine. So I will just show some demo actually, how to train this network. So this is simple 2-layer network I defined actually. So which is so there are 2 network, as I said. One is the generator network, and then other is a discriminator network. So what I have done is this one is written in PyTorch, but you can written in any other language also, or TensorFlow also. So basically, I will go through this code and then run it actually, and show actually how the images are generating. So with respect to the previous slide actually, so basically what we are trying to is generate the synthetic images by feeding the noise vectors and using the GAN network. So basically we are randomly sampling the noise vector, pass it through the generator and generate this fake images. and both fake and real images is passing through the again discriminator network, and discriminator is to train to distinguish between whether it is a fake or real. So that part of the code is written actually here. So for example, generator network is a two-layer network. First, initially, what I've done is weight and bias parameters for the neural network is defined, and this is just a two-layer network. Is first functions are defined, and for a discriminator also, two-layer network is defined here. So you can see that this is the first layer, and then it's passed through the again one more network. And then it will be passed through the some iterations. So here some 10,000 iteration we pass it so that it will try to generate the images properly. So for example, first we feed the noise vector, we generate the noise vector, and also randomly sample the images from the MNIST database, and noise vector is passed to the generator network, and it will generate a fake sample, and it will again pass it through the discriminator. So the discriminator out will be deepfake, and similarly real images also it will be passed to the discriminator network. So this is how we do the forward pass, and then there will be a backward pass also is there here. And similar step is done for the generator also. So randomly sample the noise vector and pass it through the generator network, and again pass it through the discriminator network. So we get a fake samples, and then we use the cross entropy based loss functions. So just to illustrate, I'm just saving those functions here actually in the out folder actually. So printing those values actually how training is happening, and saving the images after passing it through. I will just run those function actually. Yeah, so it passed through the first iteration, and it will give the some loss values, both the discriminator loss and generator loss. And you can see that the iterations happened, and for every 1,000 iteration, I am saving the images, generated images. So for example, I will just open that folder, out3 folder. So now here images start generating. So can see initially actually nothing is generated actually. Can see that the generated output will be very random noise, because the input will be noise actually, and over a period of number of epochs it keeps synthesizing images. So after one epoch you can see that it's trying to learn something, some distribution it's learning, but still it's not able to distinguish whether it's some digit or not. So after some epochs you can see that after again 1,000 epochs something is coming out actually. So now see, you can see that like after 4,000 iteration you can see that some numbers are coming out actually. So 0, 3 and something you can see actually. So as you train more and more iterations, you can see that the images are start generating actually. So you can see 1, and here also 3 is generating, so 9. So like this you can see that there is a improvement, and as we train more and more epochs, you can see that numbers start generating. So this is a simple demo to show actually how the images are can be trained using the GAN. Like here actually I used a very simple network, like 2-layer network for both the discriminator and discriminator, like generator. But it can be very complicated, and you can, and when you use very high deep neural networks, then maybe like then quality of the images synthesis also will be good actually. For example, if you generate like if you have a very deep convolution GAN actually, DCGAN, I mean if you use a convolution network instead of feed forward, then people call the term called DCGAN, or deep convolution GAN. So you can see that there are around 4 layers are there, 4 layers CNN is used, and the noise vector is upsampled for a different dimension. Like after first layer it is upsampled to 4x4 into 1024 dimension. So similarly we, after each layer it is upsampled, and finally you can see that 64x64 dimension image is generated. And discriminator also, instead of 2 layers they used around 4 like 4 layer of CNN layers, and basically they tries to downsample it so that it will generate some final in the output layer some probability value, so that whether it is a real image or for like fake image. So this is like if you use a very high network, actually deep network, then you can get a quality of images also will be good. But just to illustrate in the this talk, I just use a 2-layer network. If you see now, actually, I think it's further improved. You can see that the quality of images also is still improved, and also you can see that the loss values also it's start reducing actually. So earlier generated loss is around 7, now it's reduced to around 1.45. So still it's going on, so it may take some time. So I will just continue the talk actually. Maybe in the end we can see the results actually, like how the quality of the images comes. Any questions here?
Yeah, Nagaraj, this demonstration was really helpful actually. And since you're moving to the next section, we can take 2 questions that we already have here.
Yeah, sure.
So Azhar has asked, how did you plot the model distribution?
These images?
I think that's what he means.
Okay, this is like after taking the images, we are passing the generated samples, right? These images we can save it, and these images actually is coming in bunches of images. So those images I saved it, like it comes in this 4x4 images. So what is the output we are getting in generated? So I'm just saving it actually here. So that's what I'm doing it here. Here I'm saving it in PNG format. So yeah, so after passing like every 1000 iteration, I'm saving this images. I hope it answered, I guess.
Yeah, Azhar, if this was, if you had additional questions, then you can probably comment again. And the second question is from Raveen, and he asks, can we scale GANs beyond image synthesis for research problems in text or audio domain?
Yeah. So as I said in applications, we can do it for image, video, or like any kind of application where some synthesis is involved actually, or generation of some data is involved. There all we can use it. So I will also show some examples about speech also in the next few slides. But you can use it for any kind of generative applications. Any other questions?
Yeah, Nagaraj.
Yeah.
Hello. Yeah, I'm audible. Yeah.
Yeah.
I have one question.
Mm-hmm.
Actually, while training the GAN at the first time, like when you start the first epoch, for example, at that time, the discriminator can like classify the real or fact is very easily, because we are going to give the real images, and maybe other things we are giving the noise. So it will be very easy for the discriminator, but at the same time, the generator will be very poor at the beginning of the beginning of the training. Okay, so now if we continue like that, the discriminator will be a very powerful, like it can classify in the 100% accuracy maybe, but generator may be a very poor. But how will balance that thing while training that? Maybe you can give some intuition on that.
Yeah, I mean it depends on how we define our network. In this case, actually, I showed actually with a simple 2-layer network. Okay. But what people usually do is we can along with the 2 layers, we can add the additional layers to generate the images. That can be done so that we can make the generator very strong. So make the network layer is strong, as well as we can add additional constraint, because in the initial layer itself, it's as you said, it's not able to generate the real images, right? I mean, close to real images. So maybe we can add some regularization like L1 or L2 loss here, so that it tries to get a better quality of images. That can also be tried actually. And in some application, what we do is actually, so instead of training beforehand the discriminator, till around 1000 epochs, we will not train the discriminator network. Only generator is trained, and then after training some epochs, then we start training the discriminator. So that kind of training also we can do. I mean, there are different strategies, but these are the mainly 3 ways we can improve the generator training.
Oh, okay. Thank you. Thank you. I think we have another question in Google Meet chat.
Okay.
Yeah.
Yes,
Yeah.
we also have
sorry.
another question here by Subrat.
Okay. You can.
Datta. Yes, so if you can you take it now, Nagaraj?
Yeah. Can we generate sequential
Okay.
data, for example, sentence? Sequential, actually, they try to train the sequential training, like sentence generation and from, for example, not like a exactly sentence, but what I saw is from the input text generate the audio sequence. Actually, that is also again a sequential data actually. But the quality is still not up to the level of what conventional methods gives actually, because this is a generative training actually. So they tried actually, but still they tried with some dilated convolution layers for the defining the generative network, and it can be tried actually. But as of now, what are the strategies we are using it? It's not beating the other state of the art. So for the sequential data generation. And other question is how much data we may need to train a GAN network. So more the data, it's better always. So there is no minimum thing actually, but it depends on context. For example, if in audio actually, like 1 hour, 1 to 2 hours of data is sufficient. But again, it depends on applications. So for different application, it may be different data is required. Actually, I mean different amount of data. But always more the data, it will be we can get better quality.
Hello.
Yeah.
Yeah. Actually, my question is, let's say I have 2000 or 3000 number of images and number of classes are say 10 or 15.
Mm-hmm.
So in that case, whether it's better to train the generative network using the dataset directly, or before that, let's say that the dataset type is image.
Mm-hmm.
So, or I should use this pre-trained network to extract the features. Then only I use this generative network, because like in MNIST datasets, we have 50,000 of images.
Mm-hmm.
So, and size is 28 cross 28 for MNIST. And let's say in my case, the dataset size is 256 cross 256 cross 3. So in
Mm-hmm.
that case, which one will be the better one?
If very less data means like then maybe better is actually to use the conventional methods, because we have here we are training 2 networks, right? Actually, so better to use some pre-training methods and then fine tune maybe to for this network. But when you have more data, then this network will be helpful.
Okay. So for some class, say I have less number of images, and means the situation is like the class imbalance problem. So
Mm-hmm.
in one classes, say we have less number of images as compared to some other classes. So
Mm-hmm.
in that case, we can use this that GAN network to regenerate some images for that minority class, right?
Yeah. We can do some data augmentation, or we can give more weightage actually while training also. Like uh, basically, actually, we can to match that balanced data. We can do on adding noise or data augmentation. We can do it. Another thing is people tries to do like in each batches, right? We have to give the equal number of images for all classes, but maybe we can give more weightage so that it will always come up with that particular class actually, so that it will not unbalanced actually. So we can do some kind of training changes actually to so that that data imbalance problem will be solved.
Okay. Thank you.
Okay, so then I will.
Thanks, Nagraj. Actually there is another question in YouTube chat, but if you want to continue, I can take the question later.
Yeah, maybe like we can take it later maybe.
Yeah. Okay.
Yeah. So since we understood actually like now how to like train the GAN actually simple, I also showed actually how to train with a simple 2-layer network also. But in practical, actually for practical application, we have to use some deep neural network like this DCGAN. And there are like whatever I said is a simple network actually, just a GAN based network, but we can do the conditional also. Like for example, in second type of classes called conditional generation is there, where for example, imagine in the earlier case what happening is we are giving some random vector and this random vector generating some image, but if you want to change the characteristics of this particular image, it's not possible with this particular model. So what they done is, along with the random noise vector, they also feed the other text information. Like imagine girl with red hair actually. So then if we train this network with this conditioning nature, then we can also get this conditioning mechanism, or we can add some additional conditioning input, so that we can change the color from like gray to red, or like maybe hair length may be short, something like that we can do. But problem is we need the pair data here actually. So we need that different hairstyle for the training data. So that is required. So that's why it's called pair data in the conditional generation. And other one is unconditional generation, or like different domains are there. For example, I'm just taking the image example here, but it can be, you can think about other like audio or video also. For example, in the images, there will be different domains. For example, here the outdoor image is there, and there some indoor images are there. If you want to convert from this domain X to domain Y, then also we can use this GAN actually. And we have to slightly change the how to train this network. Then we can do this one domain to other domain conversion also, like from one domain image to other domain. So that is called unsupervised conditional generation, or like unpaired data generation. So these are the mainly three different categories actually in the GANs. So for example, in the conditional GAN, like how to add the constraint actually. So earlier what's happening is we are conditioning the noise vector only, and then generating the images. But now along with the conditioning, along with the noise vector, we are adding additional constraint, conditioning vector actually. Also for the real image also, we are adding that extra constraint before passing to the discriminator. So objective function will be changed from equation 3 to equation 4. Mathematically, we are representing like this, but while feeding to the neural network, what we do is, along with the conditioning vector, we are adding that, along with the noise vector, we are adding that conditioning vector. For example, for building structure, we need this kind of structure with a different floor structure, or the window and other stuff, like 3 floors. Then the generated image will be along with the noise vector. If we feed this condition structure, then we can generate that floor structure or the doors and all those information we can generate it. So this is image to image translation, we are doing it. Similarly, we can if we give the road map or a road structure actually, then we can convert to this kind of images. Or for example, giving the input of a vanity bag outliers, then we can generate a different varieties of like vanity bags. So for example, this will be useful for the like Amazon or those websites where actually they want different styles and different variations in the images, so that to attract for the people. So we can do this kind of, or maybe for architecture purpose also, we can to get a varieties of data, we can use this conditional GAN. And imagine like there are some other application also. For example, in the first column, what I've done is they have a different type of images generated from the GAN. For example, imagine there are, these are the Z11, Z12, Z13 are the different noise vector, and with that they generated these images. These are all GAN images, and if you combine all this vector, we are getting this man with glasses, some average image actually we are getting it. And in the second column, the person's images are generated without glasses. So these images generated without glasses. And in the third column, what there is female images or women images without glasses is generated. So now if we combine all three noise vector, then we are getting like, imagine man with glasses, man without glasses, means we are differencing that and then adding to the woman with glasses. So we can get different images of women with the glasses. So this kind of variations we can get it. So these are some different applications in images. So next I will tell about the unsupervised learning actually. So I was saying in the previous case, it is a paired data we need from same domain we used to transfer. But can we move from one domain to other domain? For example, in the domain A, there is a images of zebras, several images. So can we convert into horse images? So that is the we can do it using the GAN alternative called CYCLEGAN, or maybe like there is another GAN called star GAN also. So there are different variations. How it's trained is so from domain A actually where zebras images are there, we convert into generate the horse images, and that is a fake image in domain B by passing to the generator. And usually in the conventional GAN, what we do is only this GAB and DB will be there. So discriminator will try to distinguish between fake image and the real horse image. So if you see here, the fake image generated is still has the zebra's information, because it's not in same domain. This domain is different, and horse is in different domain, right? So still we can see that some zebra information is there still here in this image. So what they have done is they added one more neural network and converted this image to again back to zebra, that is domain A. So now we can easily compare these two using the L2 laws. They try to distinguish between these two, domain A and the reconstructed image, so that the training is better and also is able to make it closer to the horse image actually. So similarly, we can convert from alternative ways. For example, from horse to zebra also we can do. So this is how they try to do or improve the learning for the in the different domain images. So in addition, actually, I will just show in the speech application. Like someone was asking how to do it in speech, right? For example, imagine a source is in one domain, maybe like a male speaker, and target is in a female speaker. So if you want to convert from one speaker to other speaker in the spectrogram level, so for example, we go from this source spectrogram to target spectrogram, and we compare that using the discriminator. And discriminator, the output of the synthetic target will again pass it to one more generator, and we again back to the original source spectrogram. So now here we can compare it both each other. Similarly, from target spectrum also we can convert using the generator to synthetic source image, and again pass it to the generator to get back again to the target spectra. So here again we can do the comparison with each other, target and the synthesized target. So this is like a cyclic is happening, right? So that's why they call it CYCLEGAN. So it is one complete cycle is happening from source. It is go to target, basically synthesized target, and then from target again going back to the source. And here they are comparing each other in source domain, as well as similarly the reverse way also we can do from target to source and source back again to target. So this is again one more cycle. So this kind of learning is called CYCLEGAN. So here we can go from one domain to other domain. For example, here in happy emotions are there, the spectrogram of happy emotions are there. We can convert into maybe like a normal emotion, or like a angry emotion, or maybe for the different style of speaking. Also we can do it. So these are the some applications in speech actually. So just what I've done is I try to do the speaker conversion, like female to male or male to female. So I just play some samples here using the CYCLEGAN I tried. So this is female input we are giving.
After such a fall as this, I shall think nothing of tumbling downstairs.
So this is a female speaker, the spectrogram what I was showing. This is source, and target is generated is like this.
After such a fall as this, I shall think nothing of tumbling downstairs.
So basically we are converting from female, from gender conversion we are doing. Similarly, another example.
But I was done with the shore the day my Nautilus submerged for the first time under the waters.
But I was done with the shore the day my Nautilus submerged for the first time under the waters.
So here basically we are doing from female to male conversion. So I have another example where male to female also is happening.
And said he would go and consult his master.
And said he would go and consult his master.
In another moment down, Alice went after it. never once considering how in the world she was ever going to get out again.
In another moment down, Alice went after it, never once considering how in the world she was ever going to get out again.
Yeah, so this is how we can using CYCLEGAN, we can convert from one domain to other domain. Like in this example, I shown it for gender conversion, but we can use it for different application like emotion conversion or something like that. This is actually last year where I got these results, but still now actually the advanced one GAN is came like called star GAN, where further improvement can be done actually. And also, if you use the neural vocoder, still further quality can be improved with these results for this. So this is an example for voice conversion or the speaker conversion. So then another application for speech is using GAN for the vocoder. Like, can we convert from spectrogram to speech? Can we do that? So recently, parallel waveGAN is proposed from Ryuichi. So here in this method, what they tried is completely neural based vocoder, like spectrogram to waveform level they generated, and they got mean opinion score of around more than 4 in the scale of 1 to 5. They got around 4.5, 4.15, which is almost close to natural recording. And it supports both the single speaker and multi-speaker training, like multiple speaker also we can train with that actually. And even model size is also less actually, so that we can use for real-time application also. And it is real-time, like inference time is very real-time both in CPU and GPU, so that it can be used for some applications in either in mobile or some places we can use it easily. So just like this is actually how it is used actually as a vocoder. Any questions? Okay, so in this example, don't worry about the very complicated figure. So imagine the previous example where we are just feeding the noise, random noise vector. So in addition to that, we are adding the auxiliary features, that is conditioning input. And the conditioning input is here in a spectrogram. So from spectrogram, we are converting to the waveform actually here directly. And again, a discriminator is there to compare, and natural speech. So this is a real speech, and the generated one is a fake speech. So, and in order to distinguish that, we are similar to what I was saying earlier. There is an adversarial loss and discriminator loss. But along with that, they added one signal processing based loss called STFT loss in a different resolutions, so that the quality of the speech is good. Actually, without using this signal processing losses, the quality is very bad. But after adding this losses, they got a very good results. So what I have done is I use this method to convert from for cloning for the Shah Rukh Khan voice actually. I just used around 30 minutes of data. I basically what I have done is I trained one base model with around 10 hours of data, and then I just take 30 minutes of Shah Rukh Khan voice and with which is English data, and then try to clone it for the Shah Rukh voice. For example, here.
Thank you for calling Airtel customer care. How may I help you?
So this is an example where Shah Rukh Khan is speaking like a customer care voice actually. So so just using 30 minutes of data, we can convert and use it for any text to speech conversion. Similarly, we can I just used English data, but I didn't use Hindi, but still I is able to speak Hindi data, Hindi text or Hindi language.
अगर एक हफ्ते के अंदर या आपके अकाउंट में वापस रिफ्लेक्ट नहीं होता तो आप हमें कभी भी कॉल कर सकते हैं और हम तुरंत आपकी समस्या का समाधान करेंगे.
There is slight English accent is there because I didn't use any Hindi data. That's why it's there. But with just 30 minutes of data, we can use it for the some voice cloning application. And this is again a GAN based. Since the talk is on GAN, so I just added this one here. So any questions here?
We have some questions which were posted a while ago, so we can take them at the end, or we can take some.
Or we can take it now also, yeah.
Okay, I'll just go ahead then. So Subrat Datta had asked, how efficient would a GAN model be in semantic segmentation, keeping in mind the cost of computing?
Semantic segmentation. Is it possible to explain more about that actually? What exactly semantic segmentation means?
Subrata, are you here?
They're in the call. I mean, cost of computation will be there always, but since it's a neural based networks, some cost will be there always. So it depends on actually what kind of data is there and what is the model size. Maybe we can optimize the model size based on application. But it's like very generic question. If I get some more details, I can tell you.
Yeah, maybe by the end of the talk, if he has more questions, he can add more comments.
Okay, sure. Yeah.
And there is one more question, which is also not specific to the section you just talked about, but Ravin Sharma has asked, could you please give some insights on how Zapr manages gigabytes of TV viewership data?
TV viewership, okay, but that is basically they have a lot of like servers actually, so they get the data from different domains. They used to collect the data and then like whatever the data we are getting, right, like in the different TVs and others, so they used to collect those data actually and so store it in servers and analyze those data for some different applications.
Okay, thank you. I think we can go. We can move ahead, and then at the end, if there are more questions, I can like read them out again.
Yeah, sure.
Actually,
Sure.
one question is in Google chat box.
Okay, I'll just check it.
Nagaraj, you can take, I think.
Yeah. Is it possible to change speech of one channel, say microphone data, to speech of another channel, say telephone channel? Yeah, if you have data, then we can do it actually. So if you have some training data from one channel, we can do it. Maybe like some problem may come because if the sampling rate is different. For example, telephone channel usually will be in 8 kilohertz, and in first channel, if it is a different sampling rate, maybe we have to do some bandwidth extension or the bandwidth reduction. Then maybe we can use it, which can be used for this. You can use CYCLEGAN or StarGAN. Like StarGAN may be better actually. So it's in one domain to other domain. So in spectrogram level, we can convert from one domain to other domain. Okay, so any other questions? Okay, so I will just move to slides then. Yeah, so I showed actually like application both in image and also speech, some audio samples I played. Like looks like very promising actually, but is it actually always easy to train the GAN network? But like it's always easy, or some issues will be there. So I just list out some issues and then maybe like how to like train it better actually. So for example, one of the main issues is it will not converge actually. Usually in the conventional methods, what we do is if the loss curve is reduced to less than some value, then we try to stop the training, right? But here actually sometimes it will not converge also, like or sometimes it will diverge also, depending upon how we select the parameters. Instead of converging in the global minima, it may converge in local minima. So this problems will be there, and also it depends upon how actually our hyperparameter be selected. So, and this is also is a common, because this is a min-max problem actually. So similar to the game solving approach. So it's always equilibrium is not achievable actually. So sometimes depending upon the network, it may not converge also. So maybe we have to use some strong generator and strong discriminator, like then maybe we can get a better results for this non-convergence issue. Also, sometimes what happens is mode collapse can happen actually. For example, in the first row, what is shown is actually we generated different image samples. So, and in the different steps actually, like 10K steps, 20K steps, and 50K steps, and 100K steps. So if the training is happening properly, so the first row is shown is where the training is happening properly. So if you see in after some epochs, you can see that there is a improvement in the images synthesis. So, and this training is going perfectly fine. But sometimes what happens is it may like if data is imbalanced, there are some other issues. It may collapse to particular mode, and it keep generating the same for all the images. So for example, here it is tries to fit to the number 6 actually. So this kind of problem can happen actually sometimes. So this mode collapse issue is also sometimes happen. And the other problem is this is common also in other places, like vanishing gradient can happen actually. For example, discriminator is if it's a discriminator is very strong, then it can happen that it's very successful and it's easily able to distinguish whether it is a real image. So then it will give value of 1, or a fake image, it will give a value of 0. Then the gradient will be very low actually. So then gradient vanishing can happen actually. So these are the some common issues we can face while training the GAN. So for vanishing gradient, we can do weight clipping actually. For example, when the weights are actually going above some threshold, like for example C, then we can clip the gradients and then train the network. So that can be tried. And also there is a paper called Vegetation GAN that is actually proposed in 2017. So that also give better results. Or we can apply some kind of penalty while learning the loss functions. Along with the conventional adversarial loss, we can add additional loss called gradient penalty. So that can be tried to improve the training mechanism. And also we can apply some kind of normalization, like spectral normalization, so that gradient will be like less than some value actually. So by this kind of strategies, actually we can improve the training, and also we can solve some of the issues which I said in the previous slides. So that's actually the overall like how to train the GAN network and what are the issues we can get it. So that's about. And in summary actually, so GAN is actually similar to other machine learning tools. As I said earlier, like this is again one more tool similar to ANN, CNN, or like RNN autoencoder. So this is an alternative approach. Wherever we need some to generate some generation, we can use this GAN network, and it can be implemented using the two neural networks, generator and discriminator. And generator tries to generate the samples from the random noise as an input, and with or without conditional input. We can add additional conditional input also, which I showed in the conditional GAN. And also the discriminator tries to distinguish the samples generated from the generator, whether it's real or fake. And both are trained in tandem and also adversarial to each other. Means it's pitting against each other. Both networks is trying to fool each other. That's why it's called adversarial loss. So and then in general, actually, what I can say that most of the research problem, like whatever we are applying, like ANN, CNN, wherever we are applying, we can a GAN perspective also we can took it, and we can apply GAN in those applications. So yeah, that's the summary of GAN training and some introduction to GAN. So these are some references you can, if someone is interested, you can go through it. And yeah, that's it on my side. And if you have any questions now, we can just discuss about it.
Thank you so much, Nagaraj. And let me see if there are any more questions. Oh yeah, Subradatta has elaborated on his question, which I will take first, and then I'll go to Aniruddha's question.
Sure.
So yeah, so Subrat has asked, so his question was, how efficient would a GAN model be in semantic segmentation, keeping in mind the cost of computing? So that will be separating the ROI from the rest of the image. And
no,
yeah.
cost again depends on actually how the training network is defined. Actually, it depends on like how big the model size is there, and how we are defining the model size. It depends on that. It is we can say about the effectiveness, but without knowing the network, it's difficult to comment about that actually. About the like how we can cost, but once we get the model size, maybe we can reduce the maybe we can apply some pruning mechanism so that we can reduce the model size, and also we can apply some a way to actually reduce the model size. But before knowing that, it's I'm not sure actually about that part.
Okay, thank you, Nagaraj. I'll take it's probably the last question. So Aniruddha has asked, can you comment on the effectiveness of WGAN over GAN?
Yeah, so in the GAN, actually what happens is, as I said, sometimes vanishing gradient can happen, and WGAN is slightly stable version actually, where actually because it tries to keep the gradients within certain level. So in that way, WGAN can give better results compared to the GAN. So initially GAN is proposed, that is called, we can say it as a vanilla GAN. And then further they improved using the additional loss functions in the Weatherspoon based GAN actually. So there, the defining the loss function is different, as well as they try to keep the gradient within some level, certain level. So that's why WGAN gives slightly better results.
Okay, thank you, Nagaraj. I think I don't see any more questions, so I think that's all we have. And
questions in chat box is Google Meet.
Oh yeah, you can.
Yeah, how much?
Yeah, you have a few questions there. You can take them. If...
Yeah. How much knowledge of AI is required to use GAN network in image super resolution? I use ML algorithm for image super, but found that GAN is more superior in terms of results quality. It's not difficult actually. I mean, nowadays you can get a lot of tutorials in online, so it's we don't need some knowledge is required. But since you already worked on the image super resolution, so GAN is again some alternative tool itself actually. So just we have to define one more network called discriminator. So instead of user-defined loss function, we are adding the data-driven loss function now using discriminator. So since you already worked on ML, I think it's easier for you to shift to GAN. And other question is, could you show the final images of the model that you have trained in the demo? Yeah. So this is just a two-layer simple network. So I think let's see how it comes. It's coming slightly better and better after epochs. Yeah, this is the final results I got it actually with two-layer network, and this is how images I got actually. And this is using the GAN actually, but if you use the WGAN, you can get slightly better results. So this is using the WGAN. Yeah, this is using WGAN. And also the notice actually here we are still using two-layer network, so that we can show it within a demo actually. I mean, within talk time. So if you further increase the improve the neural network size actually, I mean, make it strong generator, then maybe you can get further better qualities. Any other questions are there? Yeah, also share the, yeah, it's there actually in the slide only. I will share the slides with AI team actually. So if you come here actually, the demo slide. So link is there in the bottom actually. So you can take the code from here. Yeah, that's it. I think in this chat box.
Yeah, Nagaraj, I have one question. Another question. Okay, so when like you talk about this min-max noise, min-max loss function. So apart from that, what other loss function generally used in that GAN training?
Yeah, it depends on domain specific. Like for example, if you are using image, actually they use some kind of additional laws like similarity laws actually. So image is structure similarity laws they use in medical images. So which is basically L1 laws. We can use all other regulation laws like L2 laws or L1 laws along with adversarial laws. But in speech, actually, what they done is for that here, right? Here actually they use short time Fourier transform based laws actually. So by adding these laws, right? So earlier without these laws, they are getting around mean opinion score of 1.2 or something, around 1.5, I think something like that. So after adding this, it's went up to 4 mean opinion scores. So still actually, even though we are using neural network based methods, by signal processing based inspired losses are still helpful actually. So these losses we can use it. And yeah, so this is the other losses.
Okay. Okay, thank you. Thank you, Nagaraj. Actually, you have a wonderful presentation. So I think all of you have learned lots of things from your presentation.
Yeah, thanks.
Okay.
Thanks AAII team for giving up opportunity also.
Okay.
Thank you so much.
Yeah, thanks all for joining.
Yeah. So, Pamir, you can take over.
Yes, so I just want to thank everyone for being here, present with us, and thank you, Nagaraj, for the time you have given us. So I think, sister, is there anything else that you want to be addressed before ending?
No.
Okay.
No.
So,
Yeah.
okay, thank you so much, and we will end the session here then.
Yeah, thank you very much. Thank you.
Thank you.
Thank you,
Bye-bye.
Nagaraj.